Hey, hi everyone. Good evening. So we are meeting after a pretty long time. So I'll give 3 more minutes for folks to join in. We'll wait for a couple of 3 minutes. 7:35. We'll start. Till then, if anyone has any questions, anything from the previous classes, we can discuss. Can you confirm if the audio is clear?
Yes, sir.
Okay, cool. Just waiting for folks to join. Yeah, perfect. So let's start then. We have folks who to join in. So I'm sharing my screen. Let me know when it is visible. Just 1 second, guys. Just confirm if the screen is visible, the OneNote screen is visible or not. Yeah.
Yes.
Perfect. So let's talk about a geometrical problem today first. So we are not going into a very specific topic today. We are just starting from scratch again because there has been a significant gap in the course, right, which we do not have. So we will start with something simple, and then we will build up towards a more complex thing. Okay. So what we are trying to build is we are trying to look at as a program or as a problem is that say there is a 2D plane on which there are two billboards already present. Okay, so we have two billboards already present, and there comes a third billboard, right, which somehow intersects the two existing billboards. So we have to figure out how much portion of the initial two billboards are visible. Okay, so let me put the question up. So what we have essentially are as inputs. So we have, say, two arrays where each array is, so a billboard is given by nothing but
Sir, your voice is breaking.
Voice is a bit low. Okay. Let's see. Voice is breaking, huh? I will try my best. Okay, voice is fine. Okay, let me know if sizable amount of people are facing any issue taking this class today from home. So there might be an issue, but if there is,
it's fine.
It's fine for now. Okay. So yeah, so what I was saying is like we have a billboard. Billboard is given by nothing but say two values. So one is the bottom left corner and one is the top right corner. Okay. So we are given say x1 comma y1 and we are given x2 comma y2. So this is how a billboard looks like. Okay. And we are already given two billboards. So there are already two billboards, say I can see from my window. So one is say a billboard like this, and one is say another billboard like this, whatever. Now somebody wants to put a third billboard up, okay, and or say something, there is a truck which moved in front of the two billboards, which is a very big truck, which whose coordinates are given to you. So the truck might look something like this. Okay, basically it will cover the view, cover our sight of line of sight like this. So say this is the truck. This is our billboard 1. This is our billboard 2, right? So we are given 3 rectangles essentially. So we have to figure out when the truck comes in, how much area of the initial billboards are visible. So how much area of the initial billboards are visible? Okay, this is the problem statement. So you are given two billboards. So where x1, y1 is the bottom left corner. So this point, x2, y2 is the top right corner. So this point, right? So B1 ka this is given, B2 ka again similar thing is given. So you are given two 2D matrices or 2D arrays as inputs, and you have three 2D matrices or 2D arrays as input. So B1, B2, and truck. You have to figure out, given the truck moves in, how much area of B1 and B2 are visible. Okay. So how would you solve this type of a geometry based problem? So think about it a bit, then we'll discuss. If anyone has any inputs, you can just unmute and talk. We can come up with an approach. So anyone can think of a logic how you want to approach this problem. Everyone got the question? So to just make things simple, I'll maybe add a bit of like a background, like the function, how it will look like. So the function that we are looking at will essentially look like this. So we'll have, say, get area, where we'll have a int b1. We'll have another matrix int b2, and we'll have the third matrix int truck. Okay, and you just have to return an int. So you have to return an int. So you have to find the area of the original billboards that is not covered by the truck. Make sense? So anyone wants to take a jab at it, take a guess how we can start. Okay, if we have to find out, okay, the problem can be also a bit different. If we have to find out whether the truck is even interfering with any of the billboards, how can we do it? So a simpler problem would have been that you have two rectangles in a 2D plane, right? You have two rectangles in a 2D plane. Can you find out whether they are intersecting or not? Can you find out whether they are intersecting or not? So if you can find this for B1 and truck, and if you can find the same thing for B2 and truck, right? So this is B2 and this is truck. Then you know that, okay, this, your answer is basically this plus this, right? So now the problem boils down to a bit simpler problem, saying that, okay, if you can find the intersections, the points or the places which have not intersected, that is the area that is remaining. So anyone can think of an idea, general idea, how we can proceed in this type of problems.
The coordinate is given.
Yeah, the coordinate is given, obviously. Yeah. So that bottom left and top right are given to you, right? So that's what I mentioned, right? These 2D matrices, these are 2D arrays which have this type of a structure. This is the bottom left corner, this is the top right corner. So you can assume that you know all the four corners, right? Nothing coming to mind? Okay, so let me explain how we can solve geometry based problem. Yeah, someone unmuted and wants to talk about it.
Sir, we can easily find the coordinate and find the area.
No, you can easily form the coordinate that is given to you. You have
Yes,
to
sir.
find the area of the non-intersection, right? So you have to find this area plus this area. So how can you easily do that? That is itself is the question. So you have to find this area. If you return an int only, so how do you figure out this area? Right? Or an even simple question that I did, even simpler modification of the question is given two rectangles like this. How do you know that whether they are intersecting at all or not?
So we can check it by checking x coordinate of billboard is in between truck. X coordinate is in between billboard or not, and y coordinate is in between or not. By that we can check that it is
There can be
intersecting.
multiple ways, right, in which they might be. So you are trying to solve whether they are intersecting or not, right? First, so you can have like an intersection like this. You can have an intersection like this. So there can be different ways how things are intersecting, right? So the truck might be upper, the billboard might be here, the billboard might be here, the truck might be here, right? Or the billboard is here and the truck is here, right? So all different combinations can be there, right? So it's very difficult to actually get an understanding of which like whether a billboard or whether two rectangles are intersecting or not. And if you have to try to find the area which is not intersecting, that is even more difficult, right? So what we generally do in these types of problems is that we try to find the surface, we try to find the whole space. Okay, we try to find the whole space. So in this case, so the whole space means this space. It's called the convex hull, or basically the bounding space, right? So we find the bounding space and then we do a very easy operation. For all the values of x1 to x2 and y1 to y2, we mark all the cells as 1. So these all the cells are marked 1. Okay. Then for this rectangle, again, for x1 to x2 and for y1 to y2, whatever the values are there, right? Because we know the bottom left corner and the top right corner are x1, y1 and x2, y2. So again, whatever the values were there, we add 1 to it. Okay. So now what is the area of the intersection? How can we find the area of the intersection? Anyone? So once we have marked them 1, and then we have not marked them 1, we have added 1. So we found the matrix first of all. Everything was 0 initially, and then we made 2 loops. One is for billboard 1, one is for billboard 2. Right? So whichever has value 2 at the end, that is this value, this is your intersection points, right? This is your area of intersection. So cells with value equal to 2. Okay. Same logic we can apply here. So this is a very, very ingenious, very, very nice logic of figuring out intersections. If there are no cells with value 2, there is no intersection. If there are some cells with value 2, however many number of cells are there with value 2, that is the area of the intersection. Okay. Same thing we can do here. We can find the maximum bounding rectangle. So with x1, x2, y1, y2, we can try to find the maximum bounding rectangle so that we can find out our constraints. So in this case, this will be our bounding rectangle, right? I'll just change the color and put it out. And then it will become very, very obvious how it will look like. So this will be your bounding rectangle. Okay. Right? This is your bounding rectangle. What do? You first, whatever the values are there for B1, you mark them as 1. Okay. And how do you do that? So you know that this point is x1, y1. And the top right corner is x2, y2. This is given to you, right? So you can just run a loop saying that, okay, for I equal to x1, I less equal x2, I plus plus, for j equal to y1, j less equal y2, j plus plus, right? You just say that matrix, you have created your own matrix ij plus equal to 1. Okay, whatever the value. Initially it was 0, you do plus equal to 1. So this you do for billboard 1. The similar thing you do for billboard 2. The similar thing you do for the truck. Okay, so 3 order n square loops. At the end, what you can do is you now search from the whole space. So the whole space, what will be this value? For the whole space, how do you run the loop? So this value will be minimum of x1, x2, and say this one was x3, x4. Right? And this one was x5, y5, and this one was x6, y6. So we will go from minimum of all the x's to the maximum of all the x's. So this is here. So this will be the maximum of all the x's. Xi. This will be the minimum of all the yi's to the maximum of all the yi's. Basically the height, right? This is the max of all the yi's. So we have to go from there to there at the end, right? So the whole search space, and we will look at only the positions which have been marked 1, right? Because these positions will become 2. These positions will become 2, right? And okay, for the truck, we don't need to, yeah. So for B1, we can add 1. For B2, we can add 1, right? And then for the truck, for the truck part, we can make it even easier for us. So we can add -1. Okay, for the truck part, we can have mat ij minus equal to 1. Okay, so this parts will become 0. This parts will become 0, and this part will become 0, these values. Right? So you'll be left only with, and these values will all become -1. So these values will all become -1, right? Which the truck has, but the billboard doesn't have. This will all become -1. So only these places will be left with +1, this side, and these places will be left with +1. So you search with on the whole surface, that is the mean of the x's to the max of the x's, and the mean of the y's to the max of the y's, and the number of cells that have +1, that is the area of the original billboards that are visible to you. Right? Does it make sense, first of all? So this is a very, very interesting geometry-based problem. So any questions? Anyone has a question? Billboards are overlapping. Okay, so the question was given like that the billboards are not overlapping. Okay, so initially you were able to see the billboards themselves directly, right? But even if the billboards are overlapping, so now the next thing is, if the billboards are overlapping, can you think of a optimal approach to figure out how much area of the initial billboards that are visible? So why I didn't want to, okay, we will not go into the billboards overlapping case because we don't know. So then we are moving into a 3D space, right? If the billboards are overlapping, that means then one billboard has to be in front of the other, right? So that is not given to us. So if you want to assume, you can assume, say that you are given another variable saying that, okay, this billboard is in front of us, like closer to our eyesight. So that is in front. So that will not overlap the other one, right? Then the problem becomes a 3D kind of a problem. Okay. So that also can be solved potentially with a similar type of a calculation. Okay, so you initially find, okay, which are the cells which are not overlapping at all, which are the cells that are visible. And then after you bring the truck in, out of those cells which are going like which are going out, which are going behind the truck. Yeah. Any questions in this geometry based problems? These problems you will see in competitions. This is probably these types of problems will be the first problems, and you have to figure out the so this will be more or less an easy kind of a problem. Okay, so once you have some expertise in geometry based problems, you will see that these are like very simple ones. And you can solve it in multiple ways. You can, if the search space is very high, so that you are thinking that order n square might be a very large loop, you can also use a map to store the values instead of a matrix, right? You can directly use a map to store the values. Yeah. So yeah, this is what I had for the first problem. No questions, then we'll move to the second one. Any questions? No? Awesome. So let's go to the second problem. So the second problem again is fairly simple. So we are looking at say I have a certain number of things that I can sell. Okay, so I have certain number of things that I can sell, and say they have prices. They have different prices available. They are different. They are at different prices, right? So you have to figure out all the possible amounts of profit I can make, right? Or all the possible amount of revenue that I can make if I sell one or more items. Okay, so these are your item prices. This is question 2. So you have the item prices given to you. You have to find out all the possible combinations of prices or all the possible combinations of revenues that you can make if you sell one or more items. Okay, so in this case, if you see that you can get, say, if you sell these two things, you can get individually. If you sell them, you can get 2 or 3. If you sell both, you can get 5. If you sell all the first 3 items, you can get 10. If you sell the first 4 items, you can get 20. If you sell the last 2 items, you can get 17. If you sell just the last item, 7, then you can, so different combinations can be there, right? So you have to figure out the different outcomes possible, and you have to return an array. Okay, so your function will look like this. So get revenue, get possible revenues, kind of a function you have to implement, where the input also is an array. The input also is an array, and you have to return an array also, right? So the input array is for the possible the prices, and the output array is basically some combination of the prices themselves. Okay. So how do you solve it? So everyone got the question? Okay, so Dhruti has come up with a solution. We can make subgroups. So how do you make subgroups and then sum it and make an array? Also, if you see the subgroup 2 plus 3 and the subgroup 5 will have the same sum. So I don't want to have the same sum twice, obviously, because that is the same revenue I'm making, right? So get possible revenues, I should have only unique values. So how do I handle that scenario also? Think about it a bit, then we'll discuss. So, okay, Dhruti has an approach in the chat. So we can take all the numbers into a string. You cannot take numbers into a string. The reason being numbers can have 2 digits, 3 digits and stuff like that, right? So it's very difficult to partition the moment you have taken them, concatenated them into a string. So if you have something like this, say 510, so you don't know if the numbers were 510 or the numbers were 510 or the numbers were 510, right? Though only this one is valid. So these are not valid, right? So it's not possible to take them into a string, but without taking them into a string, can you find the possible sums? So the question, if you can think of a very simple way, the question is you are given an array and you have to find out all the possible sums, all the possible subset sums, right? So how can you think about it? Okay, so before going into the subsets, how to generate the subsets or how to create their sums, can anyone think of the time complexity of this problem? So if you can think of a time complexity, we can think of an approach from there, right? So if you were given the problem as a simple math problem, remember in your times in class 11, 12, when you used to do real maths. So you are given a list of numbers, right? And you have to find out all the possible combinations or all possible subsets using those numbers. So how many different ways can you build that? Anyone? What can be the possible time complexity? Okay, so Dhruti has an answer n square. So anyone wants to contest that, or why will it be n square, Dhruti? Yeah, so you can either take each element or you can reject each element, right? So the moment you have n elements, so the best case will be, okay, so you don't pair with other elements technically. So when you have to look at all possible subsets, you say that your each element will be either part of the subset or not part of the subset, right? We say that each element will be either part of the subset or not part of the subset. So if you have something like this, so if you keep this as a part of the subset, other elements we don't care about, then you have some set of X combinations. If you don't keep this element as a part of the subset, you have Y combinations. Similarly for this, if you keep it, you have X combinations. If you don't keep it, you have Y combinations, X2, Y2, right? Like this. So each element has two possibilities, right? Each element will have two possibilities. Either they will be part of the subset or they will not be a part of the subset, right? So given that each element will have two possibilities, the order of complexity will be this, and this will be n times for all the n elements. There can be a little, yeah, you don't have to care about duplicates in this case. So your order of complexity will be something like of a bigger notation of 2 to the power n. Okay, so this will be your time complexity, because you can either hold the elements or not hold the elements. Now, how do you figure out the subset? So when you think about a subset, what are the two variable things? The two variable things of a subset has to be that, like, you keep an element or you not keep an element, right? So we have to have a loop starting from 0 to 2 to the power n minus 1. So if I have to solve, so these types of problems can be solved very easily in a recursive way, right? So we can just say that we will create a subset, like say subset, the given array and the left and the right values. Okay, right, n is equal to array dot length kind of thing. Okay, so we have given the left and right values initially, the left and right bounds, right? So how do we define this subset method? This subset will essentially generate all the possible subsets and then create their sums. Okay, so and initially obviously the subset the sum will also be 0. So what will we do is, so this function this will initially have the array, a left, a right, and a sum, right? So for every left and right boundaries, we will try to get a sum. Okay, so that is what we are doing here. So we will just say that if So that my stopping condition will be if the left is greater than the right, right? So if the left is greater than the right, we will print the sum, or we will add it to a final array. So we will call it, say, result, and result dot add sum, because we have completed. So there is no other way we can make that subset. So that subset is done. Otherwise, what will you do? We will do that, those two conditions that we said, right? The two conditions were there. We said that we will take the element or we will not take the element, right? So both the things we have to do. So we will call subset. So if I take that element, what will be my parameters? Quickly, can anyone tell? If I include that element, what will be my parameters? What will be my left and right if I include that element? So if I include that element, my current sum will be increased, right? Here are left if I include that element, and then obviously my subset, the remaining subsets I have to find out in the bounds. Otherwise, if I don't include the element, we are just keeping the element. In that case, we have R and we have sum itself. Right? Perfect. So these are the two conditions. So these are the two recursive cases we get. And whenever we are seeing that, okay, if L greater than R kind of thing we get, so we say that results dot add sum. Okay. So the result can be a static kind of an array outside everything. So we can have a results here, and that can get updated. It can be a list kind of thing. You can also keep the results as a set. So because I said that 2 and 3 can also give 5, 5 itself can also give 5, right? So you can use the results as a set so that it doesn't have any duplicate elements. And then you can modify them, and basically you can only add elements to the set if it is not there. Okay. So this is a very simple way in which how you can generate all possible subsets. So this also leads us to backtracking. We will not go into depth of backtracking for now. So this is a very basic application of recursion, right? Backtracking will have a separate class completely towards the end. We'll discuss backtracking in more detail. But this is a very, very simple application of recursion to figure out the number of possible subsets. The problem statement, though, was a typical competitive programming problem statement. So the problem is a bit more convoluted. So you are given a list of prices and everything, but you have to think in terms of arrays and numbers, right? So essentially you are given nothing but a set of arrays of one. Okay. Questions? All right. Okay, so very good question in chat. So could it be done in an iterative way with the same time complexity? Yes. So with in iterative way also you can build it. So because if you see this recursive way that we are building, it is going from L, it is going always to L plus 1, right? So you can have a loop, and in that loop itself, you can either take that element or not take that element and reach the end. So even an iterative way will also give you a 2 bar n kind of a complexity. Right, that's also possible to build. We will do backtracking in detail, so that time we'll look at iterative methods also. We'll define a generic way in which you can solve all types of backtracking problems. So there we will look at only iterative methods later in detail. Okay. So let's go to a third problem, and this is a comparatively easier problem. So say you are given n integers, right? You are given n integers without using extra space, and that is the main essence of the problem. Without using any extra space, can you find the number of distinct values in the list? Can you find the distinct values? Right? Can you find the number of distinct values in the list? So you are given integer, you have to return an integer, find distinct, right? And you are given an array. So you have to find the number of distinct elements in the array, but you cannot use any extra space. So you can think of using like complex algorithms which take more time, but you cannot use space. Okay, so how would you solve it? So you are given n integers. You are given n integers in an array. You have to find out what are the distinct elements. Okay, that means there is repetition. You have to find out the elements, number of elements which occur only once. And you have to do that without using any extra space. Right? So you have to do it without using any extra space. So how would you go about it? Awesome. So Atul has a solution here. So whenever you see that you have a space constraint, you can look at sorting, right? You can look at sorting the array. And the moment you sort an array, you can easily find the number of distinct values, right? So you don't need to necessarily compare adjacent elements. You can keep two pointers and move them forward accordingly, right? So if you, once you have sorted it, if it looks like this, right? So you just see, okay, this is my first distinct element. Then you come here, this is my second distinct element. So you have a count is equal to 1, then count becomes 2. Then you move forward, you see, okay, I have the same value of 2. So I don't do anything. So you can call this as prev. And as prev, as the pointer moves forward, right, you can just check whether they are same or not. So till prev is equal to 2, like till current is equal to 2, you move it forward, you take it here, then you get a new element, so you make it count 3, right? You move prev also here, then you continue to move ahead. Here again, you get a new element 4, move ahead. So you get the point, right? You get 5 and you know that there are 5 elements. So a very simple way of checking. So these are new types of problems that are coming in the space. So like if you are in a space constrained environment, if you're in a time constrained environment, right? How do you solve these types of problems? Like how do you find out distinct values and things like that, right? So if you are given space constrained kind of things, try avoiding the use of the native array.sort, right? Arrays.sort kind of thing, because they often use merge sort or quick sort kind of algorithms, which in turn uses extra space, right? So best way of doing it is, because you don't have a time constraint, you can use something like a bubble sort. So you can write your own custom bubble sort or insertion sort kind of function, very, very simple algorithm, or even selection sort, very simple algorithm to sort the array without any extra space. And then you, and after that, you can obviously build the logic for this problem. Right. Okay. So another similar problem that we will look at is, now this problem will obviously take more time. So we are given the starting and ending times of movies. Okay. So we are given an array, a 2D array, where each entry XY like this. So they are the starting and ending times of movies. Okay. So they are integers for now. You can assume they are integers. So you have to figure out, find the number of movies you can watch completely. Okay. Or you have to find out rather find the maximum number of movies you can watch completely. Right. So like, for example, if you are given the 2D array, something like this. So if your input looks something like this, 3, 5, 4, 9, 5, 8. So that means one movie is from 3 to 5, the other movie is from 4 to 9, the other movie is from 5 to 8. Then your output should be equal to 2. Which means you can watch the 3-5 movie, and when it ends, you can immediately go to the next hall and you can watch the 5-8 movie. Right? So note that you have to find the maximum number of movies, not just. So you have to, how do you ensure that whatever count you get, that is the maximum? Right. So how do you know that whatever count you get, that will become the maximum? Okay, so Atul has a solution saying that, okay, I'll sort the elements by the starting time, and if the end time greater than the starting time, the movie count plus plus. So I can refute that logic by saying that, sorry, by saying that your movies might look like this. So Atul, so this test case might, so will break your logic. So if I have a movie like this, and then I have movies like this, right? So the actual answer will be 3. The output will be 3, but your output will be 1 because you have sorted on the basis of the start times, right? So you will watch this movie, and when the movie ends, there is no other movie which has a end time greater than the start time, right? So your output will be 1, but the actual output has to be 3. Okay. So this kind of a greedy approach is not correct here. So can anyone think of a bit different solution? So Atul's solution was quite simple. He wanted to just sort it based on the start times. And he took the first movie with the first start time. So he watched that movie. Once that movie ended, he wants to go to the next movie, right? Just the small flaw with this is, do I even need to choose the first movie or not?
Sir,
Yeah.
sir, we can firstly sort it according to time. Means we can we can take an array and find the difference between every movie, and on that array, just like 3, 5, 2, and 4, 9, 5, and sort it and sort it, and after that we will sort it according to means start time, and we should do so.
So this array, you are saying you will convert it to the interval lengths.
Sir,
Then what will you do?
we will sort it according to we will
Start
sort
time.
it.
You will sort this array.
Yes, we will sort it according to means 2, 3, 5, then 3, 5, and second will be 5, 8, and will 4, 9.
I didn't get. So this is just the durations, right? So durations you will not be able to sort because you don't know which. The moment you sort them, you don't know, okay, which movie was starting from when. You just know that you have 3 movies of lengths X, Y, and Z, 2, 3, and 5.
Fusion has
Okay, there is somebody else who is saying something. Can you be a bit louder? So the starting time logic that Atul mentioned, the sorting by starting time, that will not work, right? So if anyone can think of another sorting parameter, I would want a proof. Like, can you prove definitively saying that, okay, if I sort by this, then my answer will be maximum. So Dhruti, so okay, there was a comment in chat that this is like a SRTF sort of scheduling algorithm. So SRTF is shortest remaining time first. This is not exactly like that. So there we look at multiple movies that have started at the same time. Yeah, it might have happened, multiple movies, but yeah, with that logic also can translate somehow here. But if you want to extend Atul's, or if Atul also, if you want to extend your own algorithm, the initial algorithm, right? So how would you modify it so that this case is also handled? Or my question in a different way would be, what will you sort the whole thing, the array on, such that you can ensure that you are getting the maximum number of movies? Okay, Pradosh has an answer. So he wants to sort by the end time, and then we can loop till the next start time is greater than the current finish time. Okay, so instead of sorting by the start time, I can sort by the end time, and then I can see, okay, what are the movies that are starting after the current end time. So Pradosh, can you explain, or you can unmute and explain also if you are feeling lazy to type it up. So can you explain why, or can you explain how this will always, like, it is guaranteed to give you the maximum number of movies?
Sir, we can take this example that you have shown the biggest duration of movie. If it is ending at last and if we sort by start time, then we are just wasting this whole time by watching only one movie. So if
Okay.
we'll check by the end time, then it will move to the last while sorting. So we can see those shorter duration movies. Then we can go to the means. That's why I thought by ending time it would be right.
Perfect. Okay. So say if there are two events, right? If we have two events, I'll just write down what you're thinking. So if we have two events, E1 and E2, right? With E2 say ending later than E1. If we have two movies or two events, E1 and E2, where E2 ends later than E1, it is always optimal to select E1. It is always optimal to select E1. Why? Because if you select E1, then you essentially know you have more choices to select from, because E1 is a earlier point of time than E2, right? Like what Pradosh mentioned. So if this is E1 and this is E2, because I said E2 ending later than E1, you should always choose this first so that you have more options to choose later. Right? In this case, you have no other option to choose later, and that will always be the case. Right? So we can, if we can select an event to go to after E2, then that event can also be used. Then that event we can also go after E1. So if there was another movie here, this would also have been the case. We could also watch same movie 4 after E1, right? But after E2, we can only watch M4. We cannot watch these two movies, M2 and M3, right? So we will always choose the ending time first. Whichever movie ends first, we'll choose that first, and then we'll try to build an algorithm. So these types of algorithms are called, what are these algorithms called? Perfect. So these types of algorithms are called greedy algorithms. So where you choose the best possible solution at any point of time and you move forward, right? So if you can prove that, okay, I'm done, then that is the greedy algorithm. Right? Another problem that can be in the similar space. So say I have different coins. I have coins of different denominations. And I have infinite coins of different denominations. Okay, say I have 1, 3, 4. I have only 3 denominations and I have infinite coins of each type. Right? So I want to make up an amount, right? I want to give a change for say 6 rupees. So how many minimum coins would I need? How many minimum coins will I need? Okay, so I have different coins and I have to give a change for some amount. I have infinite number of coins of each type. So how many different coins will I need? Okay, so Atul has come up with the idea that we can start selecting from max value to get the minimum number of coins. Okay, so if you start with the max value, so you start, then your answer in this case, Atul, would have been so according to Atul's logic, I'm just calling it output Atul. Okay, so it would have been, so he would select the maximum coin first. So you select a coin of value 4, then you are left with 2, right? So you cannot select the coin with value 3. So you see there is a coin with value 1, you select it. Then you are left with a value of 1. So you select another coin of value 1, right? And you're, so you use up 3 coins, right? So anyone else can think of a better output. So the actual output for this case would have been 2, where I would use 2 coins of denomination 3, right? So not necessarily doing a greedy from the largest available denomination will give you a right solution in this case, right? And why is the, so your counter question can be, how did greedy work for the previous case but not in the current case? Anyone can tell how it worked for the previous case, but not necessarily for the current case? So the current case, why it doesn't work is that if I remove the maximum possible value, right? If I remove the maximum possible value, or if I use up a coin of the maximum possible value, I am still left with 1, 3, 4, because I have infinite number of coins, but my target now is 2 instead of 6, right? And making 2 will give me, I can make 2 only by using 2 coins of this denomination. So I have basically used 1 plus 2, that is total of 3 coins, right? So my later choice in this case is dependent on the previous choice, right? But if I choose 3 directly, I would have left with 0, because I would have used 2 coins of denomination 3 and I would be left with 0, right? And I would have completed. So my each choice is determining the remaining set of choices. In the previous case, the movie times were not such that when I watch a movie, the next movie time is changing based on my current movie time, right? Current watch. So they are all fixed. In this case, we have infinite number of coins of each denomination. So the moment I use up 1 coin, my target itself is changing. My target in this case has changed from 6 to 2, right? So the problem itself is not well defined. When I say well defined, it means that the problem itself is not repetitive, right? And greedy algorithms only work well in cases where the problem is repetitive. Like in the previous case we saw, if we sorted by n times, we know that, okay, 1 movie has ended, only after that I can watch all the remaining movies that are left with me, right? All the remaining movies that are after, that starts after that n time. And obviously among those, I'll choose the smallest one because that is the most beneficial for me. In this case, choosing 4 or the largest one is not necessarily beneficial for me, right? Because I could have solved the problem with a smaller denomination directly, right? It could have been the opposite also. Say I had a denomination of 6 itself. Then with one coin itself, I could have solved it, right? I could have completed the problem. So these types of problems are more trickier. So these types of problems are more tricky, right? So you cannot solve them using a greedy approach. The greedy approach won't work because a smaller problem exists, right? So you can see here, right? So the initial problem you had was 1, 3, 4, and 6, right? How many coins you had used initially? You had used 0 coins. After that, there were 2 possibilities. One is you use 4 and you don't use 4. So if you remember the first solution that we discussed today, and that's what Dhruti also mentioned in chat as an approach. So we have either we use 4. So if we use 4, we have used up 1 coin. So we have 1, 3, 4, and we are left with 2. Or I don't use 4. Or I don't use 4. Then still I am left with 1, 3, 4, and 6. Right? So this is basically my same problem. And this is a smaller dimension of the same problem. So this is a smaller scale of same problem, right? So this is also known as optimal substructures. Okay, an optimal substructure is a smaller scale of the same problem that can exist, right? So if you took 3, you would have got 1, 1, 3, 4, and 3. If you took 1, you would have got 1, 1, 3, 4, and 5. So all these possible choices were there to you, right? Now from here, again, you could have broken it into multiple possible choices. From here, you could have broken it to multiple possible choices. From here, you could have broken it to multiple possible choices. Like this, your tree would have expanded. And the smallest height of the tree, right? Basically, the smallest root to leaf path would have been your answer. Because at every time you are reducing the target by one denomination, any one of the denominations, right? So it is again a 2 to the power n kind of a solution, right? So this is again a 2 to the power n solution. And in every 2 to the power n, you are at the end, you are getting this number. So you have to find the minimum value of this number. That will be your result. That will be your output, right? Now, obviously, when you do this type of backtracking, there will be multiple substructures that will be overlapping, right? Multiple substructures that will be overlapping. How? See, you have 1, 3, 4, and 2. Here also you could have got 1, 3, 4, and 2. When say I use a 3 denomination coin here, so I will have 2 coins I have used up. I will have 1, 3, 4, and because I have used a 3 denomination coin from 5, I am left with a target of 2. Right? So 1, 3, 4, and 2, and 1, 3, 4, and 2 I get in 2 places. So what is this type of a issue called? Anyone? When the smaller substructures are similar in different parts of the tree, what are these issues called? No one? So these issues are also, so these are smaller substructures, right? So, and they are all same, right? These issues are smaller substructures which are same. So they are known as overlapping subproblems. Okay, so you solve the problem here, you solve the problem here, it is the same thing. You don't need to solve it in 2 times. So if you can find the minimum number of coins I need to make 2 with 1, 3, 4, you can use that only as the answer here, right? You don't need to solve it again. So you can store it somewhere and fetch the result. So you solve it once and you are done. So these types of problems where both of these issues satisfy, they are known as dynamic programming. Okay, where when you do a recursion, you will see that one part of the recursion can be solved by solving another part of the recursion, right? So if you see that both the properties hold, like optimal substructure and overlapping subproblems, you know that you have to solve it using dynamic programming. Okay. This is so we will look at dynamic programming in more depth, but this is the essence of it. Right? A simpler example would be like, say you are trying to find the factorial of numbers. So you know that, and this is like a very common example that we use. So say factorial of 6 is nothing but factorial of 4 and factorial of 5, right? And factorial of 4 and 5 is nothing but 3 and 2, and this is nothing but 3 and 4, right? So you can see that the overlapping subproblems, optimal substructures have overlapping subproblems. So F3 is in two places. So if you can find F3 here, right? What is F3? F3 is F2 plus F1. And you know that F1 and F2 are both 1, right? You know this is your base case. So if you know that F3 is equal to 2, you don't need to further go down the tree here, right? So essentially you are not doing 2 to the power n operations, you are scaling it down, right? So you are directly saying, okay, F3, I directly know F3's value is 2, right? So if you have a hash map, saying that, okay, F1's, I'll just store the values. So this is my X and this is my Fx. So 1 is 1, 2 is 1, and then 3 you have found is equal to 2, right? So whenever your recursion comes here, you know F3, okay, F3 is directly 2, you don't calculate. Now what is here, you come F3 plus F2, F2 is 1, you directly know. So 2 plus 1 is 3, so F4 is equal to 3. The moment you get F4 3, you write it in the database or in your map or in your memory. So whenever you come here, you don't need to calculate F4. So you don't need to do this type of a calculation all over again, right? You can directly take from the hash map that F4 equal to 3. You are done. So what is F5? F5 is 2 plus 3, that is 5. You can add it up, right? And then what is F6? F6 is 3 plus 5, that is 8. So as you can see, so I did not calculate F3 again. Once I had calculated it here, this triangle, I did not calculate F4 again when I calculated this triangle, right? So my 2 to the power n operation, my 2 to the power n algorithm now boils down to an order n algorithm. Because of this, using this memory, right? Because I'm using this kind of a hash map to store the intermediate values, right? So because I'm using this kind of a dictionary or this kind of a memory, so I'm getting better results. So there is optimal, so I'm getting optimal substructure and overlapping subproblems, right? And that is how we are saving up time as well as space. Okay, so how we are saving up space? So we are not creating the whole recursion stack. That's why we are saving up space. How we are saving up time, that is pretty obvious. So we are not calculating a lot of things multiple times, right? So the same funda we are using in the coin change problem, and that is how we are solving it. Okay. So we will look at the coin change problem in more detail when we start dynamic programming. So we'll start dynamic programming from tomorrow. So be present. It's a very complex topic, and that's why you want to give it more time, even more time than trees and linked lists and stuff like that. We'll start from tomorrow itself, dynamic programming, very basics, right? And we will build it to some level where you can look at a problem and you know that it's dynamic programming based problem and you can solve it out. Okay. So I think this is what I had from my side today. I think we have 5-10 minutes left, so we can keep this for questions. So anything on your mind, because this is like we are resuming after quite some time. So anything on your mind before we wrap? Yeah. Or do you have any exams, anything in the next few days which we need to plan for, or any topics you want me to cover? Even before going to dynamic programming. Anyone? No questions. Okay. Okay. Another question I had from my side is, does anyone need the notes? So I generally scribble on a OneNote, right? So I don't write proper notes. I scribble. I just try to explain like what I am doing, and I hope that all of you are taking notes in parallel, or you are listening to it and later looking at the recording, whatever floats your boat. But do you need the notes? Then recordings are there, right? Okay. So yeah, you can look at the recordings from time to time. That should be fine. If you need the notes, do reach out. I don't have PPTs. I don't make PPTs because they don't help per se in an algorithm class. Whiteboard works just fine. But if you need specific notes, do let me know. I'll make them. If you need specific code, let me know. I'll share resources, or I'll share the code itself. Like previously, we have written multiple codes, right? So if you need them, let me know separately, and any specific problem you are looking at that didn't work. So we will look at it. Okay. So I think there are no other questions. So we'll wrap today. So all the best for the next, loops. Like we'll meet in the like your interview loops, I meant. So if you have anything urgent, let me know. Any topics need to be covered before any interviews or any selection, these things, let me know. So we'll do that. Otherwise, I'll start with dynamic programming and we'll take it from there. Okay, thank you. So there are no other questions, we'll wrap. Cool. Other questions? Thank you. Let's meet tomorrow. Bye-bye.